Welcome back, Precalcsters. Today, we get to go through everybody's favorite thing and start looking at everybody's favorite thing. In class today, we are going to be covering at least part of, if not all, of 1.2, where we're going to start discussing and kind of trying to recall all that we have to learn about graphing functions. So I'm going to call this graphs of functions. That is our main focus here. And as we go through, we're going to be looking at a few things that we'll see brought up again later in another context. But right off the bat, we're going to just review some of these things and see how much of it we need to really hit hard. So when we're graphing equation, our first topic, we'll just call it exactly that, the graph of an equation. I could give you guys a whole lot of random equations that some of them you would know how to graph, some of them you would not. If you didn't recall, EQN is my shorthand for equation. So the graph of an equation. Now, normally when you guys have graphed, you've been presented with y equals something or f of x equals something. It doesn't have to be solved like that. As long as you can find an x and a y that makes it true, we're golden. Now, it's easiest because you've done it all with y equals, that we'll typically try to start at that. But we will work with equations normally in two variables. What are the two variables we use? X and y. So we're just going to make a few little statements. We're going to make one introductory statement about the graph, and we're going to say the following. The ordered pair a comma b is a solution point, of, we'll make an equation f of x, if f of x, and I'm going to change that. What's the x coordinate here in this point? A. And if it's on the graph, when I plug in a, f of a should spit out what according to this ordered pair? B. If this point is on the graph. Okay, that's it. We call these things solution points. When you graph anything and you draw a straight line or a curve, you're literally drawing infinitely many of them, but you don't have to take the time to find all infinity of them. We let the straight line represent all of those. So, something easy that we can do right off the bat is if I give you an equation, I can ask, is this on the graph? So we'll do one quick example here, and we'll just see what that looks like. So all I need to know is, and let's pick a point, 3, negative 5, 3 comma negative 5, that ordered pair, is this a solution? SOL apostrophe N is my shorthand for solution. Is this point a solution of y equals 14 minus 6x? It is a simple yes or no answer, but we want to make sure that we can craft our evidence to show that yes because this or no because this. Now, if I want to know if that is on the graph, there's a couple easy things that we can think about. Do you guys know what the difference between true and false is? Then we are going to be so good at this, I promise. In this equation, in this point, to check, what do you think we should plug in for y? Hey, negative 5 is a y that we want to confirm. Let's check. Negative 5, I just want to know, is that really and truly equal to, and we had 14 minus 6 times, man, what do you think I should plug in for x? 3 is a good choice. All right, so if we look at this, let's make a determination. I'm checking to see if it's on the graph. Does it make it true is all we're after. What is 6 times 3 right here? 18. So we are now wondering, is negative 5, what, equal to 14 minus 18 is what? Is negative 5 equal to negative 4? No. If it's not a solution point, is it going to be on the graph? No. And I put a comma like I was going to write more, but literally just no, it's not. That's all we're asking. If it were, it would be true, always. Every point on the graph is where it was true. Are we cool with that? Okay, super duper fast then. I want to sketch some graphs. Now, if you don't know what a graph looks like right off the top of your head, if we draw it or write the equation, how do you graph it? How did I make you guys graph for the bell ringer? You made a table, right? So when we're sketching things, and we're still in the graph, so here we go, sketching with table, or sketch with table. Now, whether we work with a linear function, like the one that we had at the very start of class, or we work with a type of function that you've never seen, the same basic operations need to take place every single time. Now, as we get going with this, we have some benefits that we know just from our previous experiences in math to graph a linear function. How many points do you need? 2 points for a line. Okay, I have no idea what you guys learned last year. How many points do you need to graph a parabola? 3? I'm okay with that. What if you wanted to graph a cubic function? It really depends. Now in a calculus class, we need like 4 points to get a really good picture of it. And here you might need 20 or 30. Do you think I'm really going to make you guys plot 30 points? No, that sounds terrible. But as we look at this, there's even some harder questions. As we're looking at the tables, here's my expectation. We use 3 column. Now we use 3 columns because I want to see your work. There's going to be times, Addison checked right at the beginning, she showed me like I didn't put anything in the middle column. I'm fine with that if you can do it in your head. Remember on quizzes and tests, if I ask you to make a table and graph it, and you skip the middle column and you get all your y values wrong, am I going to give you the credit for it? No. If you show all the work and I can see where the mistakes happened, I'll be happy to give you some partial credit. But we use 3 columns. The first one is the independent variable. Independent, which is normally what? X is normally our independent variable. Okay, our middle column, whenever we graph these things, what was it on our bell ringer today? The equation, right? Equation. And this is where all your scratch work happens, so it's nice and organized and it fits within the problem itself. What about this last one? It's obviously y. But which variable? The dependent. Every time I would like you guys, if you are asked to graph by making a table, I would like you to show this table. Okay. We already did a linear function. We will do one more, but I want to try to get a little crazy here. Okay. Anything wild yet? Does all this look familiar? Have you guys done 3 column tables? Did I make you do it in geometry? I have no recollection. I don't know. Okay. Well, let's graph one. So here's our example. I want you guys to sketch one more for me. And I want to see what your 3 points look like. So I want you to sketch, which means it doesn't have to be perfect. It should be roughly about the shape of what the real graph would be, but don't take 5 minutes making straight lines and perfectly measuring your ticks. I just need to sketch. So here we go. By making a table, I want you to graph the following for me. X squared minus 2. Okay. Using only what you remember from last year, and I'm going to come around and like peek at some of your pages because I want to see what your math looks like before I show you what mine looks like. Cool. I will give you guys like 2 minutes-ish. You can talk with each other. You can work independently. We're going to listen to some of that psychedelic Western chill rock stuff while you guys do this. Cool. So a couple things. As we go through here, we're going to see that there's probably some silly mistakes that people will make. Our focus here is not graphing functions like this necessarily, but I'm really glad that we picked this one. First thing I noticed when I came around, a lot of you guys picked automatically 0, 1, and 2 as your points. How come for your x's? They're not wrong, just purely out of curiosity. Why those 3 numbers? 0, 1, 2 is really nice in some situations. Now, we're going to see something here, and I saw at least one person gave me the wrong graph. Do not erase it. If you've made a mistake, I want you to keep that mistake. It didn't magically disappear. But if you need a colored pen or something to draw the correct graph, I would have you draw the correct one on there. Yep. Oh. Gamung. All right. That's Vietnamese for thank you, because ban bao. All right. So here we go. Check it out. As we're looking, I saw everybody start with this. Now, not going to lie, and I hope this doesn't come off as offensive or a surprise, I think I'm better at math than most of you. Okay, so let me rephrase that because I honestly don't know if that's true. I know more math than you guys. Better at it is different because I've done this for a long time. Some of you are better at math than I am. You don't know as much math, so it doesn't look that way, but I promise some of you are. Okay, when we all of a sudden commit to 0, 1, 2, we are leaving ourselves open for maybe something weird to happen. Now, based on my knowledge, and I'm going to help you recall yours, what is the shape of this graph if it's x squared? I know it's U-shaped. So every U-shaped parabola has either a bottom vertex or a top vertex. Can you tell me if this vertex opens upward like a smile or downward like a frown? Why and how do you know? Positive x squared. It's 1x squared, but it's a positive one. Okay, so right off the bat, in my head, you may have got this to work out still, but you need to know where the vertex is. Now, luckily for me and you maybe, I think the vertex is going to be at 0. So if you chose 0, you're going to have it showing, but you might not recognize it. If I just choose 0, 1, and 2, and notice I've left some empty space here. Let's just check these and see what we get out of it. What's 0? I'm just, anywhere there's an x, I'm replacing it. 0 squared minus 2. Okay, how about 1 squared minus 2? Negative 1, and 2 squared minus 2. Are you sure? 4? Yep, it's 2. 0 probably looked okay on your graph, but here's my concern and why we need to be really careful and being able to recall what these look like. You guys said 3 points. I believed you. I've only included 3 points here. Let's see if we can all agree on why these 3 points will work, even though I'm trying to poke holes in your guys' logic and stuff. So I'm going to graph it really roughly. Does it have to be perfect? No, I'm going to say, check it out. Here's negative 2. Here's positive 2. Well, I'll try to make it a little bit more to scale. 2, 4. I don't think I need any more than that. You guys okay with that? All right, so roughly sketching, I'll just pick a square scale. So I'll say here's 2 as well, which means that'd be 1. And let's just see what we get. If all I do is these 3 points, I get 0, negative 2. I get 1, negative 1. And I get 2, 2. Okay, if your scale is right, you would have a hard time fitting these 3 on a straight line. Even with that said, is it possible that somebody had a wonky scale and they saw 3 points that looked to be like a straight line on their scale because they picked a scale? That could have happened. And it's completely reasonable that that would happen if you didn't think back to what you've seen about functions that look like this. I know it's U-shaped. Can somebody argue that these 3 points will in fact suffice for getting this graph? Convince me that those 3 points is all that I really need. Oh, what?
The word created, you know, that reflect near it.
Oh, it just reflects. Now, there's a lot going on here and a lot underneath the hood that if you didn't realize that this was the case, there is some symmetry here and our vertex is at 0, 0. When I plot 1, negative 1, knowing that this is indeed my vertex, it says if I go 1 the opposite direction, I get the same y value. So here, I just symmetried. And then if I go 2 away from the vertex, I'm going to get the same y value 2 away, whether it's left or right. So I get negative 2, 2. And now I can get this lovely parabola. Not anymore. Okay, it's beautiful. Now, here's my issue. 0, 1, 2 people. If my parabola, and it wasn't, but I just want you to be aware and mindful that these things could happen. What if my parabola's vertex was over here and you chose 0, 1, 2? Are you ever going to realize it's a parabola? Because you're only going to get this point, and this point, and it will straight up look like a straight line because you've missed your graph. Being aware of that this is a parabola, and eventually we'll go back over how do we find the vertex to really center our graphs. But having knowledge that that exists and that it could happen, we'll use that a ton moving forward. We'll build up that knowledge again, though. Just finding the points seem reasonable. Okay, I think I'm good with this for now. Should we get a little crazier with it? Should we try to graph one more first, or do you want to just get knocking on this? All right, so when we think of graphs, you guys have done a lot of graphing in your career up to this point. mostly with algebra 1 and geometry and algebra 2, you've seen most of the parent functions. Anybody remember what absolute values look like? So that's the bars that we put, like absolute value of 5. What's a graph of an absolute value look like? Very nice. Okay, it's a V shape, right? What about a cubic? Something like this. It's the math dance. Okay, we'll go through all those. You've seen them all. You've dealt with linears. You've dealt with exponentials. You've dealt with logarithmic. You've probably dealt with some fractiony things. Maybe. I don't remember if that shows up in algebra 2 or not. Probably. Okay, we are building up to this. When you think about all the graphing that you've done, are there any key parts of the graph that were super important? Anything that you remember having to work with? Like, I'll give you an easy example. Did anybody ever care about the y-intercept? Yeah, that's something I've cared about. Any other things? The x-intercept. Gosh, if only there were like 3 other names for it. X-intercepts, zeros, solutions, roots. So we deal with intercepts all the time because they tell us a ton of information about our graph. We are just barely looking at the graphing, small tables. We'll talk about the number of points that we need, but let's talk a little bit more about those intercepts. Okay. There are 2 different intercepts that we will encounter on our graphs. There's x and y. Now, if we're dealing with these things, super duper easy to define them. The x-intercept, for any graph that we deal with, it will always have the same form. If we're touching the x-axis, no matter where we are, what is the y value? And you don't have to sketch this. This is just for me to think, but here's a graph. I'm going to plot a bunch of x-intercepts without any numbers along the x-axis, or y-axis for that matter. Can you guys tell me the y value of each of these points, though? Zeros. So any ordered pair that we get ever with an x-intercept would have to take the form a, comma, 0. Every single time. Now, when we're asked to find these intercepts, you can do it graphically. That sucks. Don't do it graphically. It's terribly inefficient and really not very accurate either. Or you could do it analytically using the algebra. What is always 0 when we're looking for this? X or y? So if we're trying to find this, analytically, we could let y equal 0 and solve. As long as we understand that the x-intercept happens when y is 0, this is really and truly all we need to find our intercepts. Sometimes it can be challenging and factoring can get bigger and uglier, but we're not there yet. Easy way to do it. Can you guys do something similar for y-intercept? I'm going to use b as the number, but I want you to write me an ordered pair with a b in it, and then tell me how you would solve for the y-intercept. Once you have something written down, quietly chat with your neighbor and I'll me random. Give us like 10 seconds. Love it. All right, who wins? I think this calculator is freaking out. Let's see if it's not freaking out. Nope, still freaking out. Red, how would you write the y-intercept? Okay, do you guys agree with that? Yeah. If you wanted to solve for this analytically, what do? Let x equal 0 and solve it. Okay, piece of cake. That's all we have to do. You guys use the F word a lot, I assume, in your everyday lives. Okay, and you factored a lot last year also, right? That's the F word we're talking about, just for the record. How much factoring do you remember? We did a little tiny bit. Here's my challenge. I think that some of you in here, and this will happen even, like, no matter who your teacher is, this happens over the summer. Some of you remember to factor well, some of you a little bit, some of you not at all. Here's my challenge. I want to see where, as a class, we're at. Not individually, but as a whole class. I want you to find x and y intercepts. And here we go. On A, I'll pull up a graph here in a minute. And this, I think there's only going to be one. I'll pull up a graph, but I want you guys to do it without graphing it. We are looking for the x and y intercepts for the graph of x cubed minus 9x. I'm going to pause this. I want you guys chatting, communicating, working together without any guidance from me to begin with. Let's see how much you and your teammates can come up and recall about factoring. So here we go. Which intercept are we finding first, Addison? I have no preference. There's not a right or wrong. Because we need to find, just kidding. All right. So check it out. For the y-intercept, luckily we all have this understanding of a graph, and I know that if I'm at the y-intercept, the x value is what?
0.
So let's just see. When x is 0, we get y is equal to 0 cubed minus 9 times, okay, this feels silly.
0.
It's 0. All right, well, we just found the y-intercept. It happens at the point x is 0, so 0, comma, 0. It's the origin. Fine and dandy, I'm good with that. All right, hard part done. X-intercept. What should we let equal 0 here? If we're on the x-intercept. Yeah, somebody said it, the y value. So I'll plug that in. 0 is equal to x cubed minus 9x. Okay. I think when you guys factored, and you factored a lot last year, I assume, you got a lot of options available to yourselves, right? Okay, there are a lot of different ways to think about factoring. Every culture seems to develop their own format of mathematics. We're all doing the same thing, it just looks a little different from time to time. At risk of sounding like authoritarian, I'm going to take away your choice. We're going to factor the same way, like always. Okay, now, we always run through the same set of steps. Always, always, always. Simpler problems are easy to work with. Is there something that goes into both of them? Okay, GCF, there's our first step, every single time. If I factor an x out of this, what remains inside? X squared minus 9. Now, if you're struggling to see why this is, when I think of factoring an x out, I essentially think if I divide each of these by x, what would it remain? Because it's the same question. Factoring out is kind of like the division, we're just moving it outside. Okay, as I look at this, does x factor any further? No. So that one's done. I can't go any further. I'm going to keep copying x. Is there a binomial anywhere in this expression? A two-term expression. It's this. Okay, what's the sign between these two in my binomial? Subtraction, which is a difference. Is this, do you know the square root of x squared? Do you know the square root of 9? We have the difference of two squares right here. So there is a shortcut, which again, when we go to the factoring stuff, we'll review this much more. But you guys told me it was x and what? 3. So x minus 3 is one of these factors, and x plus 3 is the other. I don't care which one of these you write first. They're both the same. Okay. Now, all of this is still equal to 0, right? So check it out. You will hear me reference ZPP all the time, the zero product property. This statement is literally saying you multiply these three things together to find their product, and it's 0. That's why it's called the zero product property. If I give you three things to multiply and you get 0 as an answer, what do you know about at least one of them? One of them is 0. Could two of them be 0? Like if I'd said 2 times 5 times some number is 0. What's the third number? 2 times 5 times 0. What if I said 2, 0, and 0, and you multiply all three of those? Still 0, right? When we get to this part of the problem, each one of our factors has the potential of being 0. Now, there's some work that I'll show this time, and I'll try to do it consistently, but I will be guilty of skipping some work. Each one of these factors has the potential to be 0. So what I want you guys thinking out and thinking of is let's set each factor to 0. X equals 0, there's nothing else to do. What if I wanted to make x minus 3 equal to 0? If I wanted to solve this. So if I add 3 to each side of my equal sign, I get x is 3, right? Okay, what about this one? X plus 3 is equal to 0. Subtract 3 from each side, and I get x is negative 3. We have just found 3 possible values for x that would make this true. So we're done with it. We need to write our x-intercepts. We found one y-intercept here. Coincidentally, it might also be an x-intercept. But let's check these out. So one of them happens when x is 0. One of them happens when x is 3. And one of them happens when x is negative 3. What do I know the y value is going to be each time? 0, because we already plugged them in. We found 3 x-intercepts, we found one y-intercept. Okay, does all this look like stuff that you did last year? Okay, knowing that this is not like our main focus, the factoring part, are we okay moving forward? Okay, as long as you can plug in 0 for x or y, we're good. All right. What does it mean to be symmetric? The same on both sides of what? The middle. Kind of. So, we're going to look at symmetry in graphs. And am I going painfully slow or painfully fast? Okay. All right. I'm going to draw some symmetry here. And we're going to draw 3 little tiny graphs. 3 graphs that show some sort of symmetry. And I want you guys to tell me where they're symmetric. Again, they don't have to be perfect, but there are 3 types. I'm going to leave a little bit of space underneath, but we're going to draw 3 little graphs. Again, they will not be perfect. And I'm going to copy and paste because I can. Okay. Later in the semester, we will learn the language even and odd instead of these, but we're going to look at symmetry about a particular place right now. So, hypothetically, let's say that we have this graph, and I'll change color so it's a little bit easier. Whoa, here we go. I have this graph, and I'm going to very specifically identify one point on the graph, and I want you guys to, I'm going to make this nicer, I'm trying. That looks symmetric to you guys about something? Okay, I'm going to put a point on here. X, Y. There is a clear symmetry on this graph. And just so we can all agree real quick, it's symmetry about what? Where did I reflect, or what am I symmetric to? The y-axis here, right? Okay, so we have some y-axis symmetry. I'm not going to tell you these next 2, but we'll go ahead and write y-axis symmetry. I'm just going to say sim for symmetry. Okay, I'm going to draw another graph here. I want you to add on each of these the point that's not labeled. So I want you to find that point and explain to me what it looks like when we have y-axis symmetry. For the second one, we'll get a crazy graph that is not a function. There's a point that looks like xy to me. I want you to identify what this point is. And on the third one, I have a lovely point xy, and I have a lovely point down here. Each one of these graphs has some symmetry to it. What I want you guys to do, I'm going to spend a minute or 2, I want you to identify this point, tell me where the symmetry is, and then we'll summarize some stuff together. Is it clear what I'm asking you to do? Identify the missing point and tell me where the line of symmetry is, or what it's symmetric about or around, however you want to word that. Cool. We'll give it about a minute, and I'll see where we're at. All right. What is this point? Negative x, y. Okay. Deal. How about this point? X and negative y. All right. I imagine you're right here. What's this point? Okay. Anybody able to name that type of symmetry? It is about the origin. Nice job, you two. This is origin symmetry. Now, when we're looking at symmetry, again, I want to stress, when we deal with functions specifically, we will switch to using better language. This is not a function. It fails a vertical line test. This one is a function. Not our main focus. I just want to make sure that's there. What we see right now on the board is that there's a graphical way to think about symmetry. Now, if I asked if something is symmetric, but you didn't have a graph in front of you, how many of you really, really want to take the time to make a table and make a really precise graph so you can see if there is symmetry? Right? I also don't really love graphing. It's tedious. These are graphical tests. Now, what you guys have also done, seemingly unknowingly, I would assume, is you've also worked out the algebra tests for this. If I wanted to check if something is symmetric about the y-axis, I would be able to find that if I use this notation, y of x, do you guys see that that's the same thing as f of x? Okay, just because I named this y. Or we can, yeah, I'm debating if I want to roll with this. X and negative x produce same y. That's what you guys identified with fewer words when you identified this. If I plug in a 2 and I get 4, I know that when I plug in a negative 2, I'm going to get 4 again. Okay, x and negative x spit out the same value. How would you word this one? Whoever's phone, if it doesn't go like crazy, we will just ignore it for now. If, y and negative y produce the same what? Y and negative y produce the same x. Now you guys typically don't see functions written in terms of y, but we could. You have defaulted to doing x, plugging it in. We could swip it, flip it, switch it, either one of those. Swip it if we want to. How about this one? How do we word this one? X and negative x, if we produce the same thing, y and negative y produce the same x. This one's a little harder, right? We can replace x and y with, what does it seem like they might have switched with? They're opposites, exactly. Negative x and negative y, and have equivalents. I'm just going to say equiv, the same solution. It's just still a solution point is the big takeaway there. All right. Now, we're going to use some symmetry here. And this is our last example with it. Real quickly, and do you guys know something interesting that you consider interesting? Like, do you think you have an obscure fact that maybe nobody else knows, but you know? Jimin, tell me something interesting. Sure, but better find it interesting. Gosh, just putting on the spot. Anybody here ever gotten bored? So my kid has started complaining more and more because he's getting more language, so whatever. Two things. He went through his first existential realization this weekend. He was talking about death, and he's he's either starting to experience and understand his role in the world, or he's going goth. Either way, I'm happy and I'm proud of him. Yeah. That got way more laughs this hour than last hour. But he did ask me this weekend, he said something, he said, I don't want to die. And it's like, well, I don't want you to die either, dude, but you're just jumping off the couch. I think you'll be okay. And then the other thing was he started to say, I'm bored. And I remember years ago when I went through a phase in my years, how old I was, that I was getting bored quite often. And I realized, and I came across something that has stuck with me ever since. Do you know who gets bored? Boring people. Boring people get bored. If you're bored, it's on you. Like, if you're not doing something that interests you and that you're into, like, it's a really easy thing to fix. And if you're bored all the time, there's an obvious thing. Now, whether you're really bored or not, but Zeke's new mantra is going to be boring people are boring. Anyway, all right, here we go. I want you guys to use some symmetry to graph this. So last example of the day, I want you to, if I write the word ID, what is it standing for, or the acronym? Identify symmetry and graph it. And we're going to say sketch instead of graph. If I ever tell you to sketch, it means I'm not asking you to be crazy and like hardcore with it. If I ask you to graph a function, I want you to like make the ticks equal and all that stuff. All right. So let's check it out. We will graph it together, but my first challenge is I want you guys to identify the symmetry. So we have the lovely function. This is an implicitly defined function where instead of solving it for x or y, it's just written all together. So I want at your groups, using these algebra tests, determine if we have a function that has symmetry about the x-axis, the y-axis, or the origin. That's step one. Don't graph it yet. I just want us to determine symmetry. Would you like to try one together first?
Yeah.
Okay, so I'm going to check for origin first. No particular reason other than I have a feeling this answer is going to work well for what I want you guys to do. So I'm going to say origin, and we'll just check to see if there is symmetry here. According to what we wrote right above, if there's symmetry, I should be able to get the exact same equivalent expression if I replace x and y with what? Somebody said it loudly or quietly. Can you do it louder and prouder?
Negative x and negative y.
Good. So check it out. I'm going to replace x and y with negative x and negative y and see what we shake out with in the end. So we had a negative x minus negative y squared, and there we are. So we're just going to clean this up a little bit and see if we get the exact same thing. If we get the exact same thing, we have origin symmetry. If we don't, there is not origin symmetry. So let's check. These parentheses, I always include them when I'm substituting in, but do they really do anything here? Okay, so that's still negative x. Minus, what happens next? What's negative y squared?
Y.
It's positive y, because it's negative y times a negative y. Everybody okay with that? Resist the urge. You may be tempted to write plus here, but GEMS or PEMDAS says the exponents happen first. So I know that that's going to be a y squared equals 1. Is this exactly what we have here? No, we have a minus y squared, but we have a negative x. That's not the same. All of a sudden, we can then conclude, therefore, no. There's no origin symmetry. We're seeing if it's the exact same. I want you guys at your tables to check for y-axis symmetry and x-axis symmetry analytically like this. We'll see where we're at in a minute. I have a 3-minute timer too. I need more. You guys remember my diamond timer? Mm-hmm. So I used to have one that was filled with diamonds. First day of school last year, I was bragging about it and how cool it is. Dropped it on the floor, dropped 100 carats worth of diamonds. They're gone. Cool. 1 minute. Determine if there's symmetry.